shape does hemoglobin actually have, sigmoidal? Because it's cooperative. So now what would it look like? Hyperbolic, right? It would look like myoglobin. Now we can fine tune also how hemoglobin is loaded on, or how oxygen is loaded onto hemoglobin. The first way we do that is using 2,3-bisphosphoglycerate, right? 2,3-bisphosphoglycerate, we see the structure back here. And notably, about 2,3-BPG is an important metabolic intermediate that's related to 1,3-BPG, which is in glycolysis, and 3-BPG and 2,3-BPG. Glycerate derivatives are actually very important metabolic intermediates. In this case, 2,3-BPG has a -5 charge. It's got 2 negatively charged phosphoryl groups and 1 negatively charged carboxyl. And this is important because 2,3-BPG is a negative allosteric regulator, and it does that by fitting in that pocket formed in HbA only in the T state, right? So here we see hemoglobin in the T state, right? We can see the same thing back here in the T state. We have this pocket. 2,3-BPG fits in this pocket and stabilizes the T state. How does it stabilize the T state? Well, if we examine the residues surrounding that pocket, what do we see? Well, here we zoom out. What is this? Here we see a zoom in of that, right? So here's 2,3-BPG in the pocket. Here are all the residues surrounding that. What do all these residues have in common? They're positively charged, right? So lysines got pK about 10, all right? Histidine in this context is pKa about 8 or so, right? So, yeah, right? So these will all be positively charged. Okay? And what does that mean? Well, what type of interactions then can form between these positively charged residues and 2,3-BPG? Yeah, ionic interactions, salt bridges, right? Now, what happens to that pocket when we switch from the R state to the T state? What happens to the pocket? Closes, right? And 2,3-BPG can't fit in there. So what do we have to do to 2,3-BPG when we go from the R state to the T state? Yeah, gotta get rid of it. But what do we have to do for that to happen? We have to break all these salt bridges. We have to break all these ionic interactions. That's going to require energy. So 2,3-BPG being present, right, stabilizes the T state. Stabilizes the T state by forming all these salt bridges, right? So it makes it harder to go from the T state to the R state. So if we look at the graph then, right, at the loading curve, which way is 2,3-BPG going to shift that curve? Is it going to shift it to the right, or is it going to shift it to the left? Raise your hand if you think it's going to shift it to the right. And to the left? All right. So why would it shift it to the right instead of to the left?
I believe it's more cooperative, so the L50 would probably be...
Well, it doesn't necessarily have to do with cooperativity.
If the T state is more stable, then it will be better for releasing oxygen.
Correct. If the T state is more stable, it will be better at releasing the oxygen because it binds oxygen less well. But let's come back here. Remember, where is the T state binding curve? Here. And where's the R state binding curve? Here. Right? So if we had a hemoglobin that was totally in the T state, it would look like this, or totally in the R state, it would look like this. So by stabilizing the T state, we kind of average this in stronger or more. So we're shifting to the right. Okay? Stabilizing the T state. And if we look at 2,3-BPG, or at hemoglobin rather, if we look at hemoglobin in the absence of 2,3-BPG, what we see is that its loading curve looks exactly the same as myoglobin. In fact, it delivers only 1% more oxygen than myoglobin does. Myoglobin, 120 can deliver 7% of its oxygen carrying capacity. Whereas here, hemoglobin in the absence of 2,3-DPG could deliver only 8, right? In reality, in our blood, we find 2,3-DPG in roughly equal molar amounts with hemoglobin, right? So that it shifts the curve to the right, it stabilizes the T state by fitting into this pocket, making the transition from T to R less likely, right? Meaning that it wants to bind oxygen not as strongly, so we can deliver, like we've seen before, 66% if we look at 20 torr versus 100, right? Now we can also modify hemoglobin's oxygen carrying capacity by expressing different isoforms of hemoglobin, right? So we have HbA, that's adult hemoglobin. We have fetal hemoglobin, okay, that's expressed during fetal development. So would you expect HbF, fetal hemoglobin, to bind oxygen more tightly or less tightly? Less tightly, why? Huh? In embryo, they're not exposed to oxygen. Yes. What famously don't fetuses do? Breathe, right? But what also will they need? Oxygen. They need oxygen to generate enough energy to grow a whole ass person, right? So where are they going to get that oxygen from? From the mom, right? So, okay, where is the oxygen going to be found in the mom? Hemoglobin, right? All right, so now the fetus got to get the oxygen from the maternal hemoglobin. How's it going to do that? Has to steal it, like a parasite, right? So what's going to happen here? Fetal hemoglobin has a higher affinity for oxygen than HbA, right? Reason being, now when the maternal HbA and the fetal hemoglobin come together, right? Now, between the two, the fetal hemoglobin wins and grabs the oxygen. And how does it do that? Well, it's ingenious. It's a single mutation in the beta globin, which we now call gamma globin. So now we have an alpha-2 gamma-2 tetramer, right? And the mutation is very simple. It's a histidine 143 mutated to a serine, right? Histidine 143 to a serine. And why would that matter? If we come back here, notice that in the two beta chains, histidine 143 is the histidine that's participating in the interaction with 2,3-DPG. If we change that to a serine, will the interaction with 2,3-DPG be stronger or weaker? Weaker, right? Because now there is no longer a positively charged histidine there, so we lose two salt bridges. So the interaction is weaker. Does that mean going from T to R is easier or harder? Easier, right? So now we still have to kick out the 2,3-DPG, but it's not being held as hard. So going from T to R is easier. So which one will be stabilized then? R or T? R is stabilized because getting to R is easier, right? So which way does the curve shift? Does it shift to the right or to the left? To the left, right? Exactly what we see here, right? Fetal red blood cells shift to the left because of that histidine 143 mutation, make the transition from T to R easier. Now, acidity and carbon dioxide also help deliver oxygen. In the case of pH, right, acidity, that's called the Bohr effect. The Bohr effect is simply down to, again, pKa, right? We look at the loading curves for pH 7.4 and 7.2. We see a pH 7.2, we're able to deliver 11% more oxygen than we have at 7.4. This is useful because where do we find acidic tissues? Huh? Say that loud. Tissues that are metabolizing, right? And what do we call that? Exercise, right? So when we're exercising, we're metabolizing fuels, we're undergoing lactic acid fermentation, that reduces the pH. We're also producing carbon dioxide. As long as oxygen is present, carbon dioxide is converted into carbonic acid in solution, which lowers the pH as well. So at lower pHs, right, here we see one example of how the Bohr effect actually works, is this proton here. So here we have a histidine 146 in the beta chain. In the same beta chain, right, this is able to form a salt bridge with aspartate 94. Right? This is the same chain. only if this is protonated. This is going to be protonated, of course, at low pHs. And when this is protonated, this helps to stabilize the ionic interaction between histidine 146 and lysine 40 in another alpha chain. Okay, when this is stabilized, okay, what do you think is going to happen? Well, now, if this is only possible in the T state, now the T state is stabilized because we have this ionic interaction stabilized by this hydrogen bond. So going from T to R is more difficult. So the T state is stabilized and we shift to the right and we can deliver more oxygen. Okay, this is just one example, but this same kind of pattern where protonation at low pH allows the formation of hydrogen bonds or the breaking of ionic interactions leads to the stabilization of the T state so that it can deliver oxygen. Now CO2 can also promote oxygen delivery in another way, right? So of course CO2 is going to promote oxygen delivery by lowering the pH by converting to carbonic acid. But here, right, CO2 also directly interacts with the N-termini of all four of the globin genes. So the 2 alphas and the 2 betas, of course, are all going to have amino termini. These interact with carbon dioxide to form something called a carbamate, right? This carbamate, which is a carboxyl, of course, is negatively charged, and this is always at the interface between an alpha and a beta, right? The amino terminus is always at that interface. By becoming negatively charged, right, that also forms a ionic interaction that is only possible in the T state, right? So by forming this carbamate, we stabilize the T state, making it harder to go to the R state, and thereby releasing more oxygen. You can see that here in the graph at the bottom. All right, so at pH 7.4 and 7.2, as we saw before, all right, of course we can deliver more oxygen at pH 7.2. That's essentially the same graph we saw over here. But now, even at pH 7.2, if we now add carbon dioxide, this of course is going to affect the pH a little bit, right? But also, it's going to form this carbamate. Now we can deliver 88% of the total oxygen values to hemoglobin, right? And this is good because where do we find, again, acidic tissues that have a high concentration of CO2? Well, these are tissues that are undergoing a lot of metabolism. So they're using a lot of energy, which means that they need more energy, which means, of course, that they need more O2. So we should prioritize delivering as much oxygen as possible. All right. Defects in hemoglobin are disastrous, obviously. For example, we have the E6V mutation, which leads to HBS, sickle cell trait. Okay? And why is this so bad? Right? Well, E6V, this is how we normally talk about mutations, right? So you might see this in the text, or might refer to it. E being the amino acid that is supposed to be there at what position? In this case, 6, right? And then the amino acid that it's replaced with. So E6V is an aspartic acid, not a glutamic acid, at position 6 being replaced with a valine, as we see here. The fetal hemoglobin mutation generating the gamma chain, that would be H143S, right? So histidine at position 143 being converted. So why is this mutation so weird, right? Well, as it happens, position 6 on the beta chain is on the surface of hemoglobin. Coincidentally, on the beta chain of hemoglobin, there is also a phenylalanine and a leucine at positions 85 and 88 respectively, which are partially accessible. So this creates a little bit of a hydrophobic patch on hemoglobin, which is normally there, right? It's not anything detrimental, that's normally there, but there's nothing usually that interacts with it to be detrimental until we have a valine at position 6 and another beta globin gene. Because now we have two hydrophobic surface residues, or surface patches, interacting with each other. These are forced together by the hydrophobic effect, and now these two are linked together. Of course, we have two beta globin genes on each hemoglobin, right? So now we have this other valine 6, which can interact with a phenylalanine hydrophobic patch from another hemoglobin. That hemoglobin has another valence 6, which can interact with another hydrophobic patch, and so on and so on. So we start building this chain of hemoglobin. And this chain of hemoglobin forms only in the T state. deoxygenated hemoglobin. So when in sickle cell anemia, right, when we have low concentrations of oxygen, we form these fibrils, and what happens when these polymers, these fibrils, are formed? It sickles, right? So it goes back and forth between being regular shaped to being sickled. Where in the body do we normally find low concentrations of oxygen? Assume that now we're not talking about exercise. Where would we normally find lower concentrations of oxygen? Extremities, right? They're farther away. By the time the hemoglobin gets there, a lot of the oxygen's already been used up. So sickle cell anemia leads to sickle formation in the extremities, right? So this causes painful, or pain generally in the hands and the toes. Okay, what else? These sickle cell shapes, what do we learn from the case study? What's so different between the regular shape and the sickle cell shape red blood cells? They can't pick up oxygen as easily. I suppose, yeah, but they sickle because there's less oxygen already. Right? But what property do these sickle cell shapes have?
They sort of stick to the side.
Yeah, they're stickier, right? The enzymes that are found on the cell surface of these, for some reason, when they sickle, are able to bind better. So they stick to the walls of our capillaries and our veins. And what happens when we have a lot of red blood cells that stick to capillaries or veins? What is that called? Blood clots, right? Called blood clots. One of the other effects of sickle cell anemia, of course, is blood clotting. All right. Now I think we are going to get to the case studies just by happenstance. I think we should. All right. So let's go over some practice problems first. Before we get there, any questions about binding or hemoglobin? All right. So let's start here. All right. Changing pKa. So let's think about an aspartate residue. Right. So let's draw an aspartate residue here. Let's say that this is part of a polypeptide. Right, so this is an aspartate residue in a polypeptide. Right? What is the pKa? Let's just go off the table. What's the pKa of this guy here? Roundabouts. 2, 3-ish. Right? Let's just say 3. Right, let's just call it on the table. Now, similar to what happened with that histidine, where the pKa magically changed because I told you so, right? Now let's examine why it changes. Can we predict how it's going to change based on the environment that the residue finds itself in? Right? So let's see that we bring a lysine near. Is the pKa going to go up or down? Right? So let's say that this loops around, does some weird thing, but over here, we have a lysine, okay? And what is the structure of a lysine? What do we know about a lysine? Broad strokes, I don't care how many carbons. What does it end with? Huh? An amino, right? So let's just say over here, and then we have H3N, right? Now let's call it H3N plus because the pKa is so high, right? So it's most likely going to be protein. We can change the pKa to an extent, but we can't change it from 10 to 7, right? So let's just call it NH3 plus. What's going to happen to the pKa of this? Take a second. What's going to happen to the pKa? In other words, what is the pKa really describing, right, in physical terms? And what's going to happen to that value if we bring a lysine here. So down.
Well, because of the amino group has more hydrogen and pKa is basically very, I guess relatively talking about the concentration of hydrogen, so if you're adding in a higher concentration of hydrogen, it would probably be.
Alright, so we have to be careful there, okay, because we're talking about pH, which is the concentration of hydrogen. Now, that's not entirely correct. We say that pH is negative log of the proton concentration, which we write as H plus. Hydrogen has one proton and one electron, so H plus is just minus the electron, which is the proton, right? So we're talking about this proton concentration, it does not necessarily have to do with hydrogen. So just because there's hydrogens over here from the amino group isn't going to do anything about the pH or anything like that. Right? Well, let's start with this question. What are the two ways that this could exist? Well, it could exist like this, right? COO minus, or it could exist like this, COOH, right? Good? Which one is better? Huh? Protonated? Why do you think protonated? Why more stable? No negative charge? Okay. Are there any interactions now here between these two guys? No, right? We have a positive, but then we have nothing over here. Okay? What about now? Do we have an interaction between those two? Okay, so we have a positive over here and a negative over here. So is this a favorable interaction or an unfavorable interaction? Favorable, right? So we have favorable interaction between these two, right? So what does that mean then? Which state is going to be more stable? The proton on this oxygen or the proton over here? Out and about. Out and about, right? So what can we say then in English about the tendency of this proton to leave? Is it going to be higher or lower? It's going to be higher, right? The tendency of the proton to leave is higher. So does that make that more acidic or more basic? More acidic, because the proton is more likely to leave, right? And what happens to the pKa of a more acidic compound? Is it higher or lower? Right, lower, right? So we see that now bringing a positively charged residue over here is going to increase, or rather decrease, the pKa, make that proton more acidic. Now what happens if we do the same thing with a glutamate? Okay, so here we have glutamate, which also ends like that, right? So let's call it, right, make our lives easier. Let's just say that we have, right, this is deprotonated, okay? That glutamate is deprotonated. What's going to happen to pKa of this? It's going to go up or down? Up. All right, well, let's draw again our two states. You have CO minus like this, right? Or we have COOH like this. Which one is better? Which one's more stable? This or with CO minus? This way, right? Because with the minus, now we have a minus next to a minus, and that's an unfavorable interaction, right? By protonating this, now this is lower energy, it's more stable. So what do we say then about the propensity for this proton to leave? Is it going to want to leave as much? No, right? So now we have the opposite situation. The proton wants to stay here. So yes, in this case, the pKa will go up. Right? Now what about this last one here? If we move this around, right? So that this, which let's say was on the surface of a protein, is now on the inside of a protein. Right? So it used to be on the surface of a protein, and now we find it on the inside of a protein. Would the pKa go up or down? Huh? You think up? Why up? protein we talked about in chapter 2 is mostly non-polar, right? Now we move that aspartate in to the inside. Well, now we have a polar residue in a non-polar environment, which isn't great. But even worse would be if that polar molecule or polar residue were charged, right? So we have a polar and a non-polar environment, not ideal, but now we have to pick between charged and uncharged. So we'd rather for it to be uncharged. So we want that proton to be there. So that propensity of the proton to leave now is lower because it's going to remain attached here, right? So the pKa will increase, right? So you can see that depending on the environment that we find, we can change the pKa values of residue, which is why now we go back to that distal histidine over here. Even though we find it at pH 7.4, it remains protonated, right? What types of residues would you imagine are surrounding this histidine? Remember, the nominal pKa is 6.0. And now let's say we want to raise it up to about 7.5 or so. What kind of residues would you imagine? They're going to be hydrophobic? Why? All right, possibly. See someone else who hasn't spoken. Yeah.
Because the proteus state is positively charged, and positively charged interaction is favorable when surrounded by negatively charged amino acids.
Okay, sure, exactly. So if we're surrounded by negatively charged amino acids, or no, if we surround, well, let's see. If we're surrounded by negatively charged amino acids, would the histidine be protonated or deprotonated? Well, we want it to be in the N+ state, right? The N+ state is the unprotonated state, which means that we wouldn't be able to form this hydrogen bond. So we especially wouldn't want negatively charged residues around it. So what could we do? Well, we could put positively charged residues around it. Because if we put positively charged residues around it, now when it's deprotonated, we'll have a positive histidine next to a positive residue, say lysine. That's unfavorable, so the more favorable would be to have a protonate, right? So we raise the pKa. So likely, if you examine the structure of the F helix, what you'll find are that adjacent residues to this distal histidine are going to be things like lysine, okay, things that are positively charged.
If you deprotonate it, isn't it negatively charged?
No, histidine can be N+, or it can be NH. NH plus or N. What did I say? Oh, so we would want. Oh, I'm sorry. No, you are correct. We would want negatively charged. Sorry, brain fart. Yeah, we would want the NH plus version. Right, so we would want negatively charged residues around it. That's my bad. Good catch. That's a good catch. Okay, now let's finish up with this one, I think. I did want to get to the hemoglobinemia, but I do want to go over this, right? So how much oxygen can actually be delivered in hemoglobin? We move from 100 torr to 25 torr. For this, we need to introduce the degree of cooperativity, because so far, all we've talked about is this reaction here. R plus L yields RL. So in this case, R would be hemoglobin, L would be oxygen, PO2, and RL is oxygen or oxyhemoglobin, right? But, of course, what do we have? We have hemoglobin plus 4 O2 yields RL sub 4, right? So we take our fractional saturation curve, 1 equals L over L plus L50, or PO2 divided by PO2 plus P50, right? Because now what we have is not L. We have 4L. We have to raise it to the power of the stoichiometric coefficient. Reason being, right, this is all based on this substitution, Kh is equal to RL over R times L, which of course is raised to the fourth power. Right? So if we do that same process, same derivation, we raise L to the power of, in this case, 4. Right? Same down here, and because it's 4 different interactions, we raise the P50 to the fourth power as well. Right? Now, as it turns out, this is not the case, right? Because what is this implying? This is implying if we have hemoglobin and 3 O2s, nothing happens. Or if we have hemoglobin and 1 O2, nothing happens. But if we have hemoglobin and 4 O2s, we immediately bind everything and we're good. Right? Now that's clearly not the case. We can bind 1 oxygen, 2 oxygen, 3 oxygens, whatever. Right? So this exponent here ends up not being equal to the stoichiometric coefficient, and instead is something that we call the Hill coefficient, or the degree of cooperativity, right? So our fractional saturation for a receptor that binds multiple of the same ligand cooperatively becomes Y equals L to the power of n divided by L to the power of n plus P50 to the power of n. All right. Now, in the case of hemoglobin, n is usually equal to something like 2.8. Right. So now figuring this out becomes a lot simpler. Right. We want to figure out how much as a percentage are we binding at 100, right? And subtract from that how much are we binding at 20 or 25, whatever it looks like. Okay? 25. So now it's a matter of just plugging in numbers. 25, 25. P50 of hemoglobin, you should remember, is 26.4. So find those two values, and the difference between them is how much oxygen was unloaded from hemoglobin at 20 torr compared to 100 torr, right? So something the book doesn't do a very good job of explaining is this degree of cooperativity. Now, if n is positive, what we say is that that enzyme is positively cooperative, or not positive, if it's greater than 1, rather. If it's greater than 1, then that enzyme is positively cooperative, like hemoglobin, meaning that the first one to bind is hard, but then it gets easier and easier. If it's less than 1, it's negatively cooperative, right? Because if the first one is easy, the next one is harder, and the third one is harder, and so on. This rarely happens. I can't think of any examples off the top of my head. Right? There are really negative cooperativity. There's no reason for it to exist. Right? So though it is possible, I don't know any example off the top of my head. What do we call it when n is equal to 1? Does it exhibit any cooperativity? No. Right? That's just the equation we started with. If n is 1, that's what we have over here. So if n is 1, there is no cooperativity. So hemoglobin, or rather myoglobin, n would be exactly 1.0 because it's not possible for it to exhibit any cooperativity because it's not a multi-subunit. All right, so we'll end it there.